introduced by Dr. Davis.
All right, everybody, thanks for coming. I have the privilege and pleasure to introduce Tanner Hayes, Jesse Rhodes, and Aaron Williams to talk to you about designing a radio-controlled high-altitude glider. And I can only express to you how much work they put into this project for a very early deadline of October, was it 21st? 25th, to get their project done and ready to fly. So only a few months of time, but a lot of work. Good luck, guys.
Thank you, Dr. Davis. Welcome to our presentation on designing a high-altitude glider. My name is Tanner Hayes. This is Jesse Rhodes, and this is Aaron Williams. A little overview of our presentation. We're going to start with the mission objective. We're going to move into some background. We'll go over our concept of operations, then go into our design. After that, we'll go through our test flight and the results we got from the flight, followed by some future work, and we'll finish up with acknowledgments and questions. So our original mission objective was to design and build a radio-controlled high-altitude glider to be released from approximately 90,000 feet in the air, and then pilot it back down to Earth using a live onboard video system. I'm going to pass it over to Aaron. He's going to kind of go over why we weren't able to do all of that.
So to give a brief background first, just a little background on high-altitude ballooning. So high-altitude ballooning, as the name suggests, uses a weather balloon as its means of lift. It consists of, as you can see in the picture, a pod stack. And those pods are made of foam. And those foam pods will be covered in mylar and will house whatever sensors you might need for your particular mission. So typically these missions might consist of measuring atmospheric data. So you might have those sensors in the pods. You might also have a video camera on one or two of the pods. For our case, we had to have a release pod at the bottom of the stack. That's what housed the mechanism that let go of our glider once we got to the appropriate altitude. USI has two classes that participate with high-altitude ballooning every semester. A couple of the past classes have attempted to drop a paper airplane, so you can think of that as a glider, for a world record height. They've had a few issues, although I do want to mention that last semester they did have a senior design team that did manage to release one above 80,000 feet. That wasn't the world record, but it was pretty close. Some more background, the rules and requirements for our project. So for our control system, we wanted to use 433 megahertz. That signal, the FCC, the governing body that governs the airwaves for the USA, dictates that you have to have an amateur radio license for that frequency, and that it can only be a maximum of 1 watt. For the FAA, the Federal Aviation Administration, they require that model aircraft, which our glider would be considered with the control system on board, would be considered one. Must remain within visual range of the pilot, and must go no higher than 400 feet. They must also not pass within 3 miles of the airport. So obviously we wanted to break the first two that I mentioned. We want to go much higher than 400 feet, going up to 90,000 feet, and we wanted to definitely go out of our visual range. To do that with our control system, you would have to have a certificate of authorization now, but to do that, that was going to take about 3 months, so that really wasn't possible to get done by the October 25th launch. They also require that the high-altitude balloons that we saw just a minute ago, each of their pods can only weigh a maximum of 6 pounds, so our glider had to be under 6 pounds. As our team, we decided upon a few other additional requirements. One of those was that we maintain video and radio control signals throughout the entire flight, and that all of our data that we recorded during the flight be backed up on SD cards. So since we couldn't get that certificate of authorization in time, we had to revise our mission objective a little bit. So it's to drop an uncontrolled version of our glider, because that would be okay without the certificate of authorization, with our live video system that we're going to use and the avionics system. And since we didn't have control, we determined that the altitude should be less. So we determined that the altitude would be 25,000 feet or something above 25,000 feet. So for our concept of operations, we have our glider here attached to our release pod, attached to the balloon. We've let it go. Once it gets up to about 25,000 feet or 35,000 feet, the glider is released by the release pod, and we're tracking it through the car. The glider continues to descend. The balloon will continue up with the release pod payload on up to 95,000 feet to 105,000 feet. This can be slightly less, sometimes more, where the balloon will burst. So the glider's probably landed by this point. We've probably maybe been able to retrieve that. And the payload after the balloon pops will parachute back to Earth. And upon landing, we can also retrieve that. So system overview. So we have our high-altitude gliders, our main system, but we decided to break that up into 5 primary subsystems. The avionics system, the video system, the radio control system, the wing, where you can think about that as the aerodynamics of the aircraft, and then the airframe. However, as I mentioned, because we weren't able to get the COA, we weren't really able to right corner of the following slides to kind of help you follow along with where we're at when we're talking about these subsystems. So with that, I'm going to let Jesse Rhodes talk to you about the avionics system.
Okay, starting out with the system design, we have the avionics system. The avionics system was built for the glider, and what was nice about it is it recorded all of our data. That was one of our goals. So in that, we had two main sensors. We had the GPS module and the altimeter. And the altimeter was not used because of a coding error, so we mainly focused on the GPS data. So one thing that we really wanted with the avionics system, we wanted to be small, lightweight, and very power efficient. And with that, we could fit it in the glider. We had less weight with batteries and everything. So that's just a small breakdown, as you can see on the screen, of the avionics system overall. As you see, we have the GPS and the altimeter. Altimeter, again, wasn't used. The data that we collected was the altitude, velocity, the longitude and latitude values. Very important. But one of the main decisions that we had to make was the brain or the microcontroller of the avionics system. And this is very crucial. This is what we're compiling data with. So we went with Arduino Uno over the Raspberry Pi, mainly because it's very power efficient, it was light, and it was cheap. So we just went on with the Arduino Uno. So moving right on to the video system. The video system is composed of two parts. We have a video system inside the glider, and then we also have a ground station that has our monitor so we can see what's going on. As you can see here, we actually take the glider and we transmit the signal to the ground station so we can actually see what's going on. Let's go into more depth here. Inside the glider, we actually have the video camera, which is a very important part of the system. It's actually built to transmit the data down to us on the ground station. We're going to transmit at 2.305 gigahertz. It's very important. It's an open frequency. We also use a home-built cloverleaf antenna to transmit the video. And of course, we have the all-vital video camera, which is the Sony Action Cam. Why did we choose the Sony Action Cam, you said? Well, it was light, it was very cheap, and it recorded live video. And while it recorded live video, it was actually recording on itself. So that was really important to us, so we could see what's going on if we ever did lose live video. So now let's go to the video ground station subsystem. This is probably one of the most vital because we're in the car, we can see what's going on. It's basically designed to receive the signal from the glider, and we would allow the live video to be recorded onto a computer connection. That's very important. We wanted to see what was going on. We also wanted to compare it to the video on board. So that's pretty important. And also we had a monitor right next to us, basically to tell us the signal strength, basically the direction that we pointed the antenna. We can see directly our signal strength and basically the quality of the video is pretty important. So for a battery decision, and this is probably one of the most important decisions for me, was from a power standpoint, was how we're going to power everything. We have one main decision, that was battery. We went with a 9-volt lithium-ion battery, basically throughout for each system. One, because they're extremely light compared to alkaline battery. The alkaline batteries are about 2 ounces. Like shown here, it's 1.2 ounces for lithium. Next, we also have a large power capacity. That's really important. Alkaline battery has about 600 milliamp hours. Lithium battery has 1,000, and it's lighter, so that's always important for our glider. It's also reliable in low temperatures, and it's very reliable under large loads, which is very important considering we have a large video system that takes up a lot of power. So now I'm going to let Tanner talk about some materials.
All right, when designing the fuselage that was going to hold all the components Jesse just talked about, we had a few design factors we really needed to look at. One was temperature. When you get to the higher altitudes, it begins to get colder and colder. Weight was probably the most important due to the FAA regulation of 6 pounds. Cost, and then also the strength, being able to hold the components and not just break apart. So we narrowed it down to 3 common choices used in model aircraft: balsa wood, pine wood, and aluminum. In terms terms of strength, obviously aluminum is going to have be the strongest. However, we found that all three materials met the requirement we were going to need. So we were pretty confident no matter which one we chose, strength-wise, we would be good. In weight, when we drew the fuselage up and started modeling the different materials and seeing which would be the heaviest and lightest, balsa wood approximately was going to weigh about half a pound compared to 3 and almost 8 pounds for the other material. Excuse me. Then for cost, we found balsa wood was also going to be the cheapest, so ultimately we built it out of balsa wood. This is the design of the fuselage. It was 32 inches long and we used a very standard truss structure down the length. The front of it was 6 inches tall, the back was 4 inches. This tapered shape is something you commonly see on model aircraft. And you can see on the bottom left picture at the bottom of the drawing, the line is a little thicker. That is representing the base plate that all the interior components were mounted to. So for some of our subcomponents, possibly one of the most important ones is the fuselage wing interface block seen on the left. This is what connected the wing to the fuselage and also added the dihedral to the wing, which Aaron will discuss here in a few minutes. In the middle, you see our camera dome. We had to stick the camera out of the front of the plane, which you might be able to see slightly on the glider over there, to ensure that we had a clear video and that things inside of the glider would not interrupt inside of the video. So we had to create a protective casing. And then on the right, you have one of our component mounts from the inside. This is actually the one that held our video transmitter inside of the plane. So when we designed it, we knew we needed to do a little bit of analysis. We used a program called SolidWorks to do that. The purple arrows you see on the top picture are the applied force, and the green arrows are the fixed geometries areas that we showed. And on the left, bottom left, you can see that the main areas of deformation were on the vertical supports. But we did find that it was such a small amount that we weren't really concerned with it. And then on the right, what we tried to do was simulate lift under a basic wing. And as we expected, the highest deformation was at the tip of the wing. And once again, it really wasn't a very large number, so we weren't overly concerned with it as well. I'm going to pass it off to Aaron to give us a little aerodynamic design.
So we need to take those avionics and video systems that Jesse talked about, put them inside of Tanner's fuselage that he just discussed, and we need to make that fly. So that's where this wing design and aerodynamic analysis will come into play. So there are three primary areas for the wing design we need to consider. That would be your airfoil, your plane form, and your structure. So the goal is to create a aerodynamically stable wing that produces sufficient lift. So the first one, aerodynamically stable, what I mean is that if you have an upset in one of your axes, so your yaw, pitch, or roll, the glider needs to be able to right itself to correct that, especially since we're going to have control over this one. And then the second part, produce sufficient lift. So I have here the equations for lift and drag. I'm just going to go over lift. It's 1/2 times the air density times velocity squared times the surface area of your wing times your coefficient of lift. The drag equation is pretty much the same equation, except instead of coefficient of lift, you have coefficient of drag. We don't have a lot of control over air. We have no control over air density. We have a little bit of control perhaps over velocity, but our primary areas of design would be the surface area of the wing and the coefficient of lift. So with that, we'll move right into airfoil. Airfoil is a pretty important part of the wing design. So I have here an example geometry of the airfoil. So the important things to note are the chord line, which is the red dashed line. That would be the length from the wing tip, or not the wing tip, excuse me, the airfoil leading edge to the trailing edge of the airfoil. You have the camber line, which is the dashed blue line. You can think about that as the how arched the wing is, or how curved. And then you also have the thickness of the airfoil. That would be just the distance between the lower and upper surface. So particularly we're interested in the max thickness of the airfoil. And then finally you have the angle of attack. That would be the angle of the airfoil relative to the wing flow. So that would change based on your flight. So just to go into a little bit of detail on each of these, looking at camber, how does that affect the equations we saw earlier? So I have here plotted in the what would be the y-axis your coefficient of lift, and then on the x-axis we have angle of attack. So as you get more camber, that was the arched nature of the wing, you're going to move up and to the left on this graph, meaning that you get a higher coefficient of lift, but you lose the potential range for your angle of attack. So your wing can't function over the same range. So we want to keep that in mind. And then also with camber, I have here plotted coefficient of lift in the y versus coefficient of drag in the x. As you get more camber, again, that more arched nature of your airfoil, you're going to move up and to the right on this graph. So strong cambered airfoil will produce a higher coefficient of lift, as we saw on the previous graph, but it will also make it so that you'll have a higher minimum coefficient of drag. give and take nature with your camber of the airfoil. And then finally, thickness of the airfoil. So as you have a thicker airfoil, you're going to see the range of coefficient of lifts at a set coefficient of drag increase. This is your drag bucket. So we really want that higher drag bucket. You can see here it's the line that's to the left. So we want to keep that high. But again, it also will increase the minimum possible drag. So with those in mind, we determined that we were looking for a moderate camber because we wanted to take advantage of that higher coefficient of lift. We also want to be careful to keep a pretty dynamic range of use. And then we want to go to a moderate to high thickness of wing for airfoil. So with that in mind, we chose the NACA 2414 airfoil. You can see here I have the plot of the coefficient of lift and coefficient of drag like we saw earlier. The NACA 2414 has a thickness of 14% of the chord length. Again, the chord length being leading edge to trailing edge at 29.5% of the chord length, and the camber of 2% at 39.6% of the chord length. So with that, with the airfoil selected, you can move into plan form. The most important aspect of plan form is the aspect ratio. Aspect ratio is simply the wingspan, tip to tip, over the average chord length. So you can see on the image here that if you want a low aspect ratio, that would be short, stubby wings. And if you want a high aspect ratio, that would be long, narrow wings. For gliders, you really want the high aspect ratio. From literature, we found that most RC gliders would have an aspect ratio of about 27. So we were only able to get an aspect ratio of 18. That's still very high. High is considered 10 range. So we're still in the very high, but due to structural concerns where the wings joined up with the fuselage, we really weren't able to get any higher. Second aspect of plane form is the dihedral. Dihedral, as you can see in the top picture, is the angle the wings make relative to the fuselage. You want those angles up slightly. That's a positive dihedral. It helps with roll stability, so if your wing starts to dip down, it will try to right itself the other way. Also a note is that there is such a thing called polyhedral. That's where you actually go out at a dihedral and then up again. That's really nice for gliders, but it's very hard to construct, so we ended up just going with the dihedral, and we have a dihedral of 3 degrees. And then finally, for plane form, we have wing form. Wing form just means are you going to have tapered wings, or are you going to sweep the wings back, are you going to have elliptical wings? We ended up going with just a rectangular wing, which you can see in the top right here. It's good for construction, ease of construction, as Tanner will discuss here in a moment about structure. It's also good for stall characteristics if you were going to control this glider. The wing roots will stall before the wing tips, meaning that you will still have control of the ailerons. So now I'm going to pass it off to Tanner to talk to you about our wing structure.
When we were constructing the wing, we looked at a few different ideas on how we would put the interior frame of it together. We decided to go with one we saw very commonly, seeing it commonly means it was probably better. So the wing was constructed with a leading edge on the front, a trailing edge on the back, and then down the length of that you'll see 2 spars down it for some structural stability. And then also down the length you see, I think it was 18 struts down the entire length of it, also added for structural stability. The part where the wing connects to the fuselage is the wing root, and then the very far end was the wing tip. So once we had everything together, we had to put together a weight budget and see how heavy we were actually going to be. We found that the glider weighed approximately 2 pounds, and the release pod that was going to drop the glider weighed roughly 1.5 pounds, giving us a total weight combined of 3.5 pounds, well under our 6-pound goal. So we were pleased to see that, just in case we needed to add anything. We had plenty of room in the weight budget. Pass it off to Jesse, who's going to talk about the project budget.
All right, for the project budget, we had some very important components that we had to purchase, and some of them were pretty expensive, like the video camera. Our total cost was $1,168. What was nice though is USI actually provides the Endeavor grant, and the Endeavor grant is really important for scientific research. We actually applied for it, and we did receive the reward of $1,096. They helped reimburse the engineering department and ourselves for the project, so that was really good. And now we're going to talk about the fun stuff, which is the results. So here's the flight day. As you see in the left-hand or the right-hand corner is us holding the glider. Now we're about to watch a video that was actually inside. So we're about to release it. See here, it's about a minute long. See here, we released. We're going to continue to descend. soon as we release, I'm gonna let Aaron talk about some things that he noticed.
So some of the things to note that we'll talk about in our results is the fact that the camera's pointed almost directly at the ground 90% of the time, as well as that we're in this really tight turn. You can see here that it's to the left, and then about a minute later, we're going to get a flip back to the right. So that's going to be important for our aerodynamic analysis too.
See here, I'm at the lane. It's kind of soft, somewhat. See, we kind of lost our limbs there. All right, so now we're going to dive right into the results and analysis. This is my favorite part. Go right into the avionics. First off, we were very successful. We had data logged on both the glider and the release pod throughout the entire flight. That was one of our goals. We checked that off. Very good. Since we had both of the sets of data, we could compare them. It's my favorite part, so there we go. We're going to compare them. You can see here, this is the altitude data. Blue is the glider. Orange is the release pod. What's cool is you can see the blue kind of drops off, and that's actually where we released. That's pretty interesting. If for some reason the glider was to fail, the avionics on the glider was to fail, please note that in orange you can see the acceleration of the altitude. So if it did fail, we could still see where we released because of the acceleration. That's pretty interesting. We just dropped payload. So just to wrap it up, we had 27 minutes into the flight, we released, and it was at an altitude of 24,480 feet. Pretty good. So let's talk about the video system results. First off, we had live video throughout the entire flight. Really important. That was one of our goals. The Sony Action Cam recorded the entire flight. You guys just saw some of that. Pretty important stuff there. We also had the live video and the onboard video that confirmed the release. We also had the avionics system that confirmed the release at the altitude that we really wanted. It's pretty good. And then finally, the live video. Some of the clips were actually recorded. We couldn't do the entire flight because of a computer error. We're going into that. Let's talk about structural results.
So when we finally found the plane after about 2 hours of searching, we found that there was only one structural failure on it. The fuselage wing interface block, where the fuselage and wing connect together, was broke, but after review of the video and things like that, we determined that it was probably broke when the plane landed and not during flight, which was promising to us knowing that it stayed together in flight. So it wasn't a huge concern, but one thing we were talking about is the potential of changing the material of this block to something a little stiffer. Passed off Aaron for aerodynamic results.
So just to briefly discuss what I think, or what we think the video shows as far as the aerodynamics. So I think it's a combination is what we're seeing. So the first thing is what we call Dutch roll. I'm not talking about these sadly, but what Dutch roll is you get your nose of the aircraft will be pulled slightly to the right, and that wingtip will be pulled slightly down. Well, you have that dihedral I talked about earlier. It'll try to right your aircraft, and then the tail will generate a little bit of lift, and you'll get a left side slip. So it repeats itself, so you get this kind of tail wagging motion back and forth. That comes from not having proper tail area. After the flight, we ran through the calculations and found our tail area should have been 27.6 square inches. However, we actually only had a tail area of 8 square inches. So quite a big deal there. You might say, though, that it's obviously not a back and forth motion, although we did see a left and right change. So I think the second thing going on is what we call static margin, or rather an issue with our static margin. Static margin is simply the dimension or the length between your center of gravity and your center of lift. So flight day we were trying to measure this, and I don't think we got it measured properly. So what I think happened is that rather than being about 12% back from leading edge like it should be, we were further forward, so that caused the nose to be pointed mostly to the ground and caused what we saw in the video. It also could be that it was just a static margin issue, that our center of gravity was just too far forward and the wings simply stalled. So there may have been no Dutch roll, but it's quite a possibility. And I'm going to pass it on to Jesse to talk about our control system design.
So for the future, and since we couldn't get the COA, we actually did design the radio control components of the glider. It's mainly in our paper, but we just would like to show you guys. Basically, the radio control design for me would be communicating with the glider so we can control on the way down. Basically, it's divided into two subsystems. We have the ground station, and we have the glider, and from the ground, we could actually use a remote control it via live video. So that would be really neat. Now I'm gonna let Tanner talk about the control surface.
All right, so after looking into what we were going to need in order to control it, we determined we would need 3 different surfaces. We would need the ailerons highlighted in green, the elevators, which are highlighted in purple, and the rudder, which is highlighted in red. The elevators are used to control the pitch of the aircraft. The ailerons are used to control the roll, and the rudders control the yaw. And you can kind of see what those entail on the picture on the right. So a basic layout of our elevator design, we're just going to use a standard control surface on the tail wing, connected to one linkage. Then the linkage would connect to where we were going to make a servo housing underneath the wing, figuring it would be the heaviest. And that's where the red linkage on the picture you see is headed towards. Didn't really fit in the picture. For the ailerons, it was the same idea. The servos that would control it were in the same area. There'd be a shaft run through the ailerons on the wing that would control them. And the picture on the bottom is kind of representing what the ailerons would do. When the servo was in plus 90 degrees, the aileron would be facing up. When it was at 0, it would be leveled out, which is in the black. And then the purple is minus 90 degrees facing down. And then for the rudder, it was the same idea as the elevators from the tail. Control surface with the linkage headed back to our servo housing. We figured all 3 of these systems would probably control it. The long-range control of it was our main concern, though. Finally, I'd like to finish with some acknowledgments. I'd like to thank our advisor, Dr. Davis. I'd also like to thank Dr. Glenn Kissel and his entire Engineering 471 and 290 class for letting us fly on their balloon. I'd like to thank Dr. Mitchell for signing off on all the different purchase requests we kept giving him. And we'd also like to thank Donna Moore for submitting all of the purchase requests that we did. We'd like to thank Mark Foisey. He was our FAA contact. And we'd like to thank Vince Frazier for getting us started on contacting the FAA and who we needed to call. And then finally, we'd like to thank Dr. Jane Johansson from Endeavor. She was who helped us get the grant we needed. Any questions? And the gliders up here if anybody wants to come up and see it.
Questions?
Yeah, I was just wondering, before you guys launched, did you do any kind of aerodynamic testing, like dropping it off on a building or something like that?
Due to the time constraints, we weren't really able to fully get the testing we wanted. We did plan on doing that, but we're not able to get the glider done quite in time to be able to do that without risking damaging the plane.
What's the skin made of?
It's called Monaco, commonly used RC hobbyist kind of thing they put on the plane. It's, I don't remember the exact material, but Monaco. He did one coating around all of the surfaces on the outside.
Can you explain how it works?
The Monaco,
Yeah.
it's applied using a heat iron. You lay it on the side and you have to very carefully iron it onto it. Aaron spent, I think, 6 hours on each wing trying to make them smooth. It takes a long time to do.
What was the total weight of the balloon that was being launched off of compared to the 3 pounds or the 2 pounds that was on it? Do you maybe that people know? What was the? I guess the question I'm getting at is the increase in acceleration of the balloon once you let it go. Was that due primarily to drag, or was that primarily to weight?
We think it was the releasing of the weight of our glider dropping off is what you saw the increase from.
Right. Was it due to the weight, or was it due to the drag reduction? Because you were.
I'm not sure. I think I lean more towards it being the weight, because I think when we dropped it, it was, I think, roughly 30 or 40% of the weight of the payload was dropped.
So, did you guys, in the run-up to designing this, did you learn anything or explore anything from Kentucky Space Friends Consortium's Mars glider that they worked on about 10 years ago, or any other kind of other gliders at other universities, or did you learn anything from, say, Wright State University that's done live video? Have you learned about any other live video that's been done from a balloon to help you in any way? I'm just wondering what you were able to grab from other universities or hobbyists on some of these issues.
We were able to grab, there was a Swedish man by the name of David, mispronouncing his last name, but it's Warstall. he actually did something very similar, took an RC plane up on altitude balloon and released it. Different release mechanism, but similar concept. Different plane design, I think it's a flying wing design. Had some issues with the live video feed, lost it too part of his flight after it dropped, just took out part of his antenna. But we were able to pull a lot from him on how he did some things. There was also a group we found earlier this semester that attempted a similar project in South Africa. They didn't go up quite as high as we wanted to go, but they actually had a similar project as well. So we were able to gain a lot of data from them because they actually had the GPS on board just like we wanted to do. So we were actually able to get that and see their velocities throughout the flight and things like that.
Did you check anything with the Mars glider?
We didn't really get a chance to check anything with the university.
Any other questions?
You might have said this, but how far from the launch point to where it landed was the plane?
Yeah, roughly 26 miles. It landed near Flora, Illinois. We launched, I think it was 26 miles, it was northwest